So the last section that we are going to cover, which is in chapter 16 in the book, is a PWM. Now, we have seen in the last section or in the last chapter about, we talked about DC motors. Now, the speed of the motor depends on three factors: the load, the voltage, and the current. So these are the three main factors. Now, for a given load, we can maintain steady speed by using a method called PWM, which is pulse width modulation. Now, by changing, or let's say modulating the width of the pulse applied to the DC motor, we can either increase or decrease the amount of power provided to the motor, thereby increasing or decreasing the motor speed. Although the voltage has a fixed amplitude, it has a variable duty cycle. So wider the pulse, higher the speed. So MCUs with the fixed amplitudes duty cycle can be controlled accurately, and it's one of the desired properties of DC motor is that their speed can be controlled with PWM very easily. And PWM goes through a low pass filter to effectively present a variable voltage or current level to the DC motors. Now, microcontrollers with PWM circuitry embedded in, all we have to do is load the proper registers with the values of high and low portions of the desired pulse, which is the duty cycle, and the rest is taken care by the microcontroller. It's quite easy, actually. And this allows microcontroller to do other things as well at the same time. So it's giving us a flexibility and opportunities. And the ability to control the speed of these DC motors using PWM is one reason that DC motors are often preferred over AC motors, because AC motor speed is dictated by the AC frequency of the voltage applied to the motor, and the frequency is generally fixed. So as a result, we cannot control the speed of the AC motor when the load is increased. So here are some examples. PWM can be generated separately by timing high and low phases of the generated waveform, like duty cycles, and alternative is to use PWM modes to relieve the CPU for other tasks. So we have seen waveform generation, which we can use that in order to increase and decrease the speed of the DC motor. But microcontroller is saying, I have another module in here that you don't need to do that. I will take care of it, and we can do something else. So this is what we are going to see, how we can use microcontroller resources in order to generate these PWM pulses. So timer 0 and timer 2, which is an 8-bit timer, has got fast PWM mode, which is one of the modes. Counter counts as in normal. So OCN is cleared, non-inverting mode, or set inverting mode on a compare match, but the counter continues counting. OCN pin is set to non-inverting mode or cleared in inverting mode once the count reaches to the bottom 0 value. And timer 1 and 3 works in a similar manner, except bottom and top values can be varied for the counter. So 8-bit, we know 0 and 256. But in timer 1 and 3, 16 bits, these are changing. So what we can do is, again, the same timer as you have seen it in the timers chapter and also in the waveform generation. Again, we have got the waveform generator. Then we just need to modify these modes and the COM bits in the timer control registers. So going back to these registers, so in the previous section, we have seen how we can use CTC and normal mode for generation. Now we are going to see the PWM modes. And again, we can clear OCN on compare match and set OC0 at bottom, which is a non-inverting mode. And also we can do set OCN on compare match and clear OC0 at bottom inverting mode. So you can see the differences over here for the fast PWM. So it will start counting in the fast PWM mode. It goes up to here. Okay, so that's the top. Now you can see that OCRN updated and timer overflow interrupt flag will be set over here, like in the normal modes. So what will happen? These are tracked down. So as you can see, OCN is always high and OCN invert will be low. Okay, so these are like based on these one of them is inverting, other one is non-inverting. So this is actually the non-inverting one, and this is the inverting version. Now, what will happen on these points? As you can see, depending on the OCR value, you can see that it's toggling. Okay, so when there's a compare match, it sets the OC0 pin at the bottom. Okay, and you can see how it is operated based on the compare matches. Okay, so over here, OCRN is updated and timer overflow flag is generated, but where OCRN is matching the values, it actually generates the waveform for us. This is how the fast PWM is working. And again, we have got the prescalers. If we need to use, we can use it. And when COM0, 1 and 0, 0 is 0, 0, then P operates as an IO port. When it is 1, 0, the waveform generator, this is important, that's why I'm repeating it again, generator clears the OC0 pin, and whenever the compare match occurs, and it sets it at the top. This mode is called non-inverting mode, and in the inverted PWM, the duty cycle of the generated wave increases when the value of the OCR 0 increases. And when it is 1, 1, the waveform generator sets the OC0 pin whenever compare match occurs and clears it at the top. This mode is called the inverted PWM, as we have demonstrated in over here. And in the inverted PWM mode, when the value of OCR0 increases, the duty cycle of the generated waveform or the wave decreases. So once again, in the non-inverted PWM, which is the top one, the duty cycle of the generated wave increases, okay, when the value of OCR is increasing. So when we have a bigger value, as you can see over here, the duty cycle is increases. But in the non-inverting one, when the value of OCR increases, which is like this one, the duty cycle of generated wave decreases. Okay, so we have to be careful on that when we are doing designs. So fast PWM, as you can see, we can demonstrate it with a example with the formulas actually that we can use. So again, OCR0, it can be set to any value. Now, one thing that we need to take care, so the highs and lows over here, the low part, which is this is the inverted version. Now it counts up whenever the OCR matches, it toggles, it changes to 1, and then it carries on to the overflow, and then whenever the overflow occurs, it toggles again, and then it counts up again. So whenever the OCR match, it toggles, and then whenever the overflow occurs, it toggles again. Now, one thing that we need to be careful over here, we are actually having 256 clocks, okay, from one overflow to the other one. This is one thing. And on the other side, it's OCR plus 1 always. Okay, so OCR value plus 1 because of the overflow. So the equations given for us is if you want to find the frequency of the wave, we just need to use the timer clock. So as the timer counts up all the time, so the complete period is 256 clocks. That's why we use 256. And as before, for the timer, we just need to use F oscillator divided by the N. And for the generated wave, it's the oscillator divided by the 256 by N. So in order to find the duty cycles in non-inverting mode, we just need to use OCR plus 1 divided by 256 times 100, and non-inverting mode, it's 255 minus OCR 0 value divided by 256. Now, the one thing about the fast PWM mode is 0% and 100% duty cycle can be achieved in the inverted and non-inverted modes respectively. But in the application, if you require a value or the duty cycle between 0% and 100%, you cannot achieve that. You should avoid it. Okay, so there are some limitations in the fast PWM as well. Okay, so you can see the again the formulas for the fast PWM with the waveforms. So OCR, as you can see, so it counts up, then OC0 and inverted version, non-inverted and inverted, so and then counts up over there and then down and so on. And this is showing another one where we have got a increased OCR value. So we'll have a increased duty cycle over here. And as you can see, decreased duty cycle in the inverted mode. And we will use these formulas. So here is the example. So we have got 8 megahertz clock, make the pulse duty cycle 75% and frequency 31.250 kilohertz in non-inverting fast PWM. Okay, so what do we need to know? We know the duty cycle, we know the frequency of the wave, and it has to be non-inverted fast to PWM. So at this point, in order to derive some expressions, let's write down the equation required. So we need the frequency of the oscillator, the wave for SOC 0, then it's going to be F clock divided by N 256. So at this point, F clock is 8 megahertz. Okay, divided by N times 256, and we know the frequency, which is 31.250 kilohertz. So now we just need to rearrange to find the prescale value for us. N is going to be 8 megahertz divided by 31.250 K times 256. So that would give us 1 as a prescaling value. And then what we can do is we can easily use the formula over here for the non-inverting mode. So duty cycle is 75 over 100. And then we have got OCR 0 plus 1 divided by 256. So if we rearrange the equation, OCR 0 plus 1, it's going to be, as a result of the simple mathematics, 192. And in this, at this point, This is going to be 0 hex C0, and OCR 0 by itself is just going to be -1 of that, which will give us 0 hex BF. And that will be the OCR value that we need to load in. And also we need to configure TCCR. So the TCCR is going to be what? TCCR 0. This is going to be 0. We don't need to force anything. VGM modes, we can go back to check it. VGM modes, it's going to be fast PWM, so 1 and 1. And then COM modes, it's going to be non-inverting, so that should be 1 and then 0 for the COM. Again, 1, 0, and we have got the VGM 0, 1 as 1. And the clock is going to be no prescaling, so 0, 0, 1. So this is 6, and this is 9. Okay, so we have to set TCCR as 0 hex 69. That will be our configuration. So that's all we need to do for fast PWM. And there we go. We have got the OCR and TCCR value based on the duty cycle and the frequency. Now, an alternative method to the fast PWM is phase correct PWM. Now, phase correct PWM, it's based on the dual slope operation. So maximum frequency can only half as large as the fast PWM, but the counter counts repeatedly from bottom to top and then top to bottom. It's quite different to fast PWM. And OCN is cleared, non-inverting mode or set inverting mode on a compare match while counting up. And also it can be OCN set, non-inverting mode or cleared inverting mode on a compare match while counting down. So two modes of operations again, and timer 1 and timer 3 are operating in a similar manner. And only the values are going to change. So if we look at this configuration where we have got phase correct PWM, again, clear OCN on compare match, set OC0 at bottom, or counting down, let's say in this case, and counting up and counting down, and this is going to be counting up and counting down. Now, if we look at over here, OCN inverted, so we start to count up to FF, okay? So when we reach this point, as you can see, without any compare match, we know that nothing is going to happen. So what will happen? OCRN will be updated and interrupt flag will be set. Then we go down and then timer overflow interrupt flag will be set. Now, at this point, we go up again, okay? And now if we have got OCRN updated, and we also have OCN flag will be set. Now, when we are moving down, if there's an OCRN over there, okay, so OCRN flag will be, interrupt flag will be set again, and OCRN will be updated. And over here, overflow will be updated. Then we have got another match over here, then interrupt flag is set, and then we go up, OCRN is updated, and then again the interrupt flag is set. So as you can see, while going up or while going down, we can generate a separate interrupts and from the OCFN. So again, counting up to the FF and counting down, like it goes up and down like a yo-yo, we say all the time. And based on that, we can easily generate the PWMs. So in fast PWM mode, phase of the wave shifts with different duty cycles. And you cannot achieve 0% duty cycle in non-inverting mode or 100% in the inverting mode. But in the phase correct mode, can be fixed and it can be between 0 and 100% duty cycle can be achieved. So if you are driving a motor, phase correct PWMs are preferred. So we can compare it and we can show the operation of the phase correct. Now what will happen with the non-inverting mode output of the timer? So it counts up when it reaches the OCR, it changes, it toggles, and then counts up to FF, and when it is going down, it reaches to OCR again, so it toggles again. And then it goes up and starts to count again. Whenever matches, it toggles, and then counts up and going down again, matches, and it toggles. So what do we have here? As you can see, from one side to the other, we have got two OCRs. So from one part or one period has got 255 plus 255, which is going to give us 510 clocks in total. So that's what we need to consider. And as you can see, for the generated wave, we are using 510 clocks and 510 clocks over there as well. So then duty cycle is going to be 255 and 255 minus OCR 0 and OCR 0 plus 1 for the non-inverting versions, because we can have 255 and 255. So we can achieve a duty cycle between those. And again, with the phase correct PWM, we can have 510. The equations for the duty cycles are given, and we can make the calculations for appropriate operation. So the questions again, so 8 megahertz clock, and duty cycle is 75% and 15 megahertz clock. So we'll have 15 megahertz, and we need to find the prescale, which is going to be 1 again, and 75 over 100. So when we rearrange the formula, we are going to get OCR as 191. Okay, so in the non-inverted mode, so 191, and TCCR will be set for phase correct PWM, which is 61. So that's all you need to do. When you configure this up, we can easily generate PWM signals. So these are the differences, as I already mentioned. So in the driving motors, we prefer to use phase correct because it can achieve 0 to 100% duty cycles. It's more efficient and more accurate. So here is the example, which will be the last example of this chapter. So we have got the DC motor control using PWM. As you can see, AVR PV3 is connected. We have got an opto-isolator in between to protect the circuitries inside of the AVR, and the motor driver and the motor on the other end. So if port A7 is 1, DC motor moves 25% duty cycle pulse at 245 Hertz. And if it is 0, then moves to 50% duty cycle. So duty cycle is going to change based on the port, and the frequency is 245 Hertz, and we have got 8 megahertz clock. So we need to do some calculations in order to get these done. If we are going to use PWM, phase correct PWM, so we have to use this equation, FOC 0, F clock divided by N times 510. So what is our values? So the frequency is 245, F clock is 8 megahertz, and N times 510. So we just need to rearrange the equation. So N is going to be 8 over 245 times 510. So this is actually going to give us 64. So our prescale value will be 64, which we will need to use. And then once we have got that, when we want to have a duty cycle as 25, that means that's going to be 0.25 times 255, which is equals to 64 for OCR 0. And when we have 50% duty cycle, 0.5 times 255, this will give us 128, which is equals to the OCR 0. So we have got the values for OCR and TCCR. How do we need to set it? So this is going to be 0. Then VGM mode phase correct is going to be 1. And the COM bits, so non-inverting or inverting, it's up to us. So let's use inverting mode. And then 0, 1. So the VGM is going to be phase correct. So that's going to be 0. And then we have got scalar as, we haven't put the scalars over here, but we can check it from here. 64 is 100. So this is 7 and this is 4. Okay, so 0 hex 74 will be used as a TCCR value. So as we have got all the information required, now only thing that we need to do is we just need to program it. So at this point, let's write the code for it. Now we need to set the port that is controlling it, which is PB3. So we can say SPI DDRB3. So set PB3 as output. Then port A to be an input, DDR A, which is port 7. So set PA7 as input. Then once we have set that one, we'll set the TCCR, so LDI R16. We have got the TCCR value as 0 hex 74 based on our calculations. And that means N is equals 64, prescaler value. It's phase correct, PWM, and it's going to be an inverted. So now we just need to say out TCCR 0 R16. And that's going to be TCCR value. So then we have to check if pin is set or not, SPI C. So skip bit if cleared, pin A 7. So skip bit, or let's say skip next if pin A7 equals 0. So at this point, if it is 0, it will skip. LDI R16 64. So if pin A7 is 1, then R16 equals 64. Okay, otherwise, SPIS pin A7. Now, what we need to do is if pin A7, skip. Next, if pin A7 is 1. And then LDI R17. It's 128. So we can say if pin A7 is 0, then R16 equals 128. And then out OCR 0 R16. So based on the pins, OCR value will be set. So OCR 0 equals R16. And then R jump L1, where we need to jump back over here and start checking it again. So that's all you need to know. That's all you need to do in order to activate the motor from the microcontroller using PWM phase correct mode. Now, if you have any questions, please note those down and you can ask me during the live session. That's all I want to say about this chapter. Thank you.